Welcome back, everyone, to the Deep Dive. Ready to get circular. Today, we're diving deep into the concept of the circular economy.
And we'll be exploring a really interesting new approach to actually measuring its effectiveness.
That's right. Using, wait for it, thermodynamics.
Yeah, it's not your typical economics topic, but trust me, it's fascinating stuff.
So I have to admit, when you first showed me this paper, Circular Economy Design through System Dynamics Modeling, my mind was kind of blown. Like, we're actually going to try and quantify circularity.
Exactly. It's about going beyond, just the warm, fuzzy feeling of sustainability. We want to measure results. How circular are we, really?
Okay, but before we get all mathy, can you maybe give us a quick refresher on what a circular economy even is?
Of course. So in the simplest terms, it's about shifting away from that old take, make, dispose model.
Right, the linear economy where resources are just, like, used up and tossed away.
Exactly. A circular economy aims to eliminate waste by keeping materials in use for as long as possible.
Closing the loop, so to speak.
Exactly. Products are designed for durability, repairability, and eventually their components are reused or repurposed. Less waste, less pollution. It's a win-win.
Definitely sounds good in theory. But the question that always bugs me is, how do we actually measure how circular a system is? Like, how do we know if we're actually making progress?
And that's where this research paper comes in with its bold idea. It proposes a new metric. They call it circularity, and they're using the Greek letter lambda to represent it. And get this, it uses thermodynamics to quantify how much unsustainable material is flowing through a system.
Okay, now I got to know more about this lambda equation. How does it work?
Well, the equation looks like this. MUB plus IOA. It might look intimidating, but each component represents a specific aspect of unsustainable material flow.
All right, let's break it down piece by piece. What's MUB?
MUB stands for the total unsustainable mass that's being transported in batches. Think of it like raw materials being moved on trucks.
Okay, so anytime a big chunk of unsustainable material moves, that adds to MUB.
Exactly. Then we have PureSAC. This one represents the continuous unsustainable flow. Like imagine wastewater being discharged into a river, that kind of thing.
So we're capturing both the big chunks and the constant streams of unsustainable stuff. Makes sense. Now, what about that, Erin?
AIM is just a time interval. Usually they set it to 1 second to keep things simple. It's there to convert the flow rate lyric into a mass so we can add it to the MUB. Got to make the units work,
Yeah, I love physics. So basically, we're adding up all the unsustainable stuff moving through the system, no matter how it's moving.
You got it. And the result, that lambda, gives you a negative value. The more negative it is, the less circular the system is.
Okay, but hold on. You keep saying unsustainable. What exactly makes a material or a flow unsustainable?
Good question. The paper defines it pretty clearly. They say a mass or flow is unsustainable if it comes from a non-renewable resource or if it ends up in a landfill, incinerator, or polluting the environment.
So basically, if we're taking it from a source that will run out or just dumping it back into the environment as waste, that's a no-no.
Got it.
I'm really curious to see how this equation plays out in the real world, though. The paper starts with a simple example. They call it the linear case.
Yeah, example 1. It's a great starting point. Imagine a single cube of material going through the classic linear process.
Okay, so like from the mine to the landfill.
Exactly. It starts with extraction from a mine, then it's transported by truck to a manufacturer, transformed into a product, shipped to the retailer, then to the consumer, and ultimately ends up in a landfill via a garbage truck.
The poster child for inefficiency.
Yep. But the really neat part is that they don't just describe it, they model each step with equations. Equations 6 through 18.
Oh boy, here comes the math. I know our listeners eat this stuff up, so let's get into it. What are these equations actually telling us?
At their core, they're describing the basic physics of how that material moves through the system. For example, equation 6 is the kinetic energy of the truck carrying material, that 1/2 MeV squared we all learned in physics class.
And the mass here, MC5, is the mass of both the truck and the material it's hauling.
Right. Then equation 7 defines the potential energy, M. They're being very specific, even defining the height, that ZIT, as a function of the distance the truck travels on a sloped path.
Getting fancy. And then equation 8 uses the good old Lagrangian equation of motion to figure out the truck's acceleration.
It considers all the forces at play, the truck's engine force, friction, even the component of gravity acting on that slope.
Equations 9, 10, and 11 then break down the truck's acceleration into its X, Y, and Z components.
Well, equation 12 is kind of interesting because it basically says that while the material is being processed at the manufacturer, its velocity and acceleration are both 0. Makes sense. It's just sitting there being transformed.
Then we move on to the ship in equation 13, which, just like the truck, has its own forces to consider, like the engine pushing it forward and the drag holding it back.
And because the ship is assumed to be traveling horizontally, equation 14 just looks at the acceleration along the x-axis. No up and down or side-to-side movement for the ship. Then, at the retailer, just like at the manufacturer, equation 15 says the material is hanging out, not moving.
And finally, we get to the garbage truck with equations 16 and 17. They're describing its motion as it takes the product to its final resting place, the landfill.
And of course, we're back to considering their same old forces of the engine and friction.
It's amazing how much physics goes into simply moving a product from point A to point B.
Right. And all of that leads us to equation 18, where the magic happens. This is where we finally calculate the circularity goal for this very linear system.
Show me the numbers.
Well, in this case, everything is moved in batches, so the AT part of the equation is 0. We're only dealing with MUB. We have 1 unit of mass, or M, leaving the mine, and 1 unit of mass entering the landfill. That gives us a MUB of 2 meter.
So our role is -2 meter, meaning 2 units of mass are essentially lost in this whole process. It's kind of eye-opening to see how even this basic example shows just how inefficient a linear model is.
It really drives home the need for a different approach, and that's where the paper gets really interesting in example 2, the case of reducing.
This is where we start playing with the circular economy ideas, right?
Exactly. This example explores 2 scenarios where things are, you guessed it, reduced. The first one imagines the manufacturer using 50% renewable materials instead of relying solely on the non-renewable mine.
So half of it's coming from a good source, half from the mine.
Right, and this change shows up in the calculation. The MUB for the mine extraction is cut in half, but the product still ends up in the landfill, so we still have a whole unit of mass there.
So the total MUM is 1.5 meters in this case.
Exactly, and that gives us a circularity of another 1.5 meters.
Which is already a less negative number than the purely linear case. So just by adding some renewables, we've improved the system.
It really shows how important material choices are. But there's another way to reduce, and that's the second scenario. They look at what happens if the manufacturer simply uses less material to make the product a 20% reduction.
So instead of 1 unit of mass, they only need 0.8 units to make the thing.
Right. And because that reduction applies to both the material from the mine and the material going to the landfill, our MUB becomes 1.6 meters.
And that gives us a circularity of 2 equating 1.6 meters.
Which is better than the totally linear case, but not quite as good as using renewable materials.
Interesting. So even though both strategies reduce material, using renewables makes a bigger difference in the circularity score. It's not just about using less, it's about using better materials, right?
Exactly. Now, the next example is where things get really cool. They introduce the idea of extending the product's lifespan, a core principle of the circular economy.
Bring on example 3, the case of robotic repair. This is where robots come in to save the day, right?
Well, sort of. In this example, they add a new step to the process, a robotic repair and second use phase. Instead of going straight to the landfill, the product gets fixed up and used again. We're delaying its trip to the dump.
Okay, but if it still ends up in the landfill eventually, wouldn't the circularity just be the same as the linear case?
That's where things get tricky and where the concept of memory comes into play.
Memory. Okay, you've officially piqued my curiosity. What's this about memory?
Well, they introduce a new notation that represents a specific time horizon. We're not just thinking about the final destination, but also how long the material is in use before it gets there.
So time becomes a key factor in the circularity score.
Exactly. In the robot repair scenario, the material stays in use for longer. It's delaying its inevitable demise in the landfill. So for a given time, the circularity is actually better than the linear scenario, even though the ending might be the same.
So even though it might eventually become waste, the fact that we used it for longer through repair and reuse improves the overall circularity. I like it.
Exactly. It challenges our thinking about circularity. It's not just about avoiding landfills entirely. It's about extending the lifespan of products.
That memory element adds a whole new layer of complexity. It's like saying the journey matters as much as the destination.
I like that. And it makes us think more carefully about product lifespans and the choices we make as consumers.
Definitely. And I'm sure we'll have even more to say about that as we continue our deep dive.
This whole idea of a time horizon that in the circularity equation, really opens up some interesting questions.
It does. It's like we're saying products have a memory, and that memory plays a role in how circular they are.
Exactly. And it makes you wonder, what's the right time horizon for different systems? Are we talking short term or long term? The answers can change depending on how we look at it.
It's like we're always looking for quick fixes when it comes to sustainability, but maybe we need to think more long-term about the whole life cycle of a product.
I think so. We can't just focus on whether something is recyclable or not at the very end. We need to think about how long it's used, how many times it can be repaired, even how its parts can be reused later.
It's about making that use phase as long as possible, not just managing the waste at the end.
Exactly. And that means changing how we design and manufacture things. No more designing for obsolescence. We need to design for durability, repairability, even upgradability.
It's interesting to think about how this time horizon might change how companies make decisions. Imagine a company has to choose between a material that's easy to recycle but doesn't last very long, or a tougher material that's harder to recycle but lasts much longer.
It's a classic trade-off, and the time horizon becomes really important here. If we're only thinking short-term, maybe that easy-to-recycle material wins. But if we're thinking long-term, the durable one might be better overall.
Which begs the question, who gets to decide what the right time horizon is? Is it the company, the consumer, the government?
It's tricky. There are a lot of different people involved, and they might have different priorities. A company might be thinking about profits, while the government might be thinking about the environment.
And consumers, well, they probably care about cost and convenience.
Exactly. It seems like we need everyone to work together to come to some kind of agreement.
And this circularity metric, with its time horizon built in, could be a good starting point for that conversation. It gives us a way to compare different approaches and see their impact over time.
It's like having a ruler for circularity instead of just arguing about what sounds good.
Exactly. It could help us make more informed decisions, both for businesses and for consumers.
I think it also highlights the importance of transparency. Consumers want to know where their products come from and what impact they have.
Having a clear way to measure and communicate circularity could help them make better choices.
Absolutely. Imagine if products had a circularity score, like those nutrition labels on food.
That's a great idea. Consumers could see that score and choose products that are more circular.
And that would encourage companies to make their products more circular, too. It's a win-win.
So this mathematical framework can actually help bridge the gap between making money and being sustainable. It's about finding solutions that work for everyone.
I think it shows that sustainability isn't just about doing the right thing. It can also be good for business.
It's about seeing waste as a design flaw, not just something that happens.
Exactly. But I think we need to step back a bit and look at the bigger picture. Even with all the math and equations, there are still challenges to making a circular economy a reality.
True. This metric is a great tool, but it's just one piece of the puzzle. What other things do we need to consider?
Well, there are technical challenges, like finding new materials and figuring out how to recycle things more efficiently.
And what are the economic and social side of things?
Those are important too. We need to think about how to make circular products affordable and how to make sure everyone benefits from a circular economy. It's a big challenge, but I think it's one worth tackling.
We've been geeking out over this new circularity metric. But let's be honest, equations alone aren't going to make our economy circular, right?
You're absolutely right. Math helps us understand and measure, but putting circular principles into practice, that's where the real work is.
So where do we even begin? What are the biggest obstacles we need to overcome?
Well, I think a fundamental shift has to happen at the design stage. We need to move away from design for obsolescence.
Right, the idea that products are meant to break down and be replaced.
Exactly. We need to embrace design for circularity instead.
Okay, I hear that phrase a lot, but what does it actually mean? What does it look like?
It means thinking about the whole life of a product from the get-go, designing things to be durable, repairable, upgradable, products that can stay in use for as long as possible.
So it's more than just picking recyclable materials.
It is. It's about designing products that can be taken apart easily so their components can be reused or repurposed.
So instead of manufactured, we should think of products as being assembled.
I like that. Thinking about products like they're modular systems, like Lego blocks, you can swap parts in and out, upgrade them.
That's a cool way to think about it. But this all sounds like a huge change, not just for designers, but for how things are made.
It is a big shift for sure, but there's some really exciting stuff happening with materials science. bio-based materials, new recycling technologies, all sorts of innovations that could help us get there.
Okay, that's promising. But even with those advances, aren't there roadblocks? Like, doesn't economics sometimes work against circularity?
Definitely. Our system is often geared towards cheap production and quick profits, so durable, repairable products might not always compete well.
It's almost like the system is rigged against being sustainable.
In some ways, yes. That's why government policies and incentives can be so important. They can help level the playing field.
So what kind of policies are we talking about?
Well, one idea is extended producer responsibility. The idea is that companies become responsible for what happens to their products at the end of their life.
So they have a reason to design them to be recycled or reused.
Exactly. It shifts responsibility from the consumer to the producer, who can actually design for circularity. There are also things like tax breaks or subsidies to encourage using recycled materials or adopting circular business models.
Good ideas. But I imagine there's pushback, right? Some industries might not like this.
Of course. Change is always hard, especially when it involves changing how industries operate. But I think it's becoming clearer and clearer that a linear economy just isn't sustainable in the long run.
The costs, both to the environment and to society, are just becoming too high.
Exactly. And that's why I'm optimistic that more and more governments and businesses will get on board with the circular economy. It's not just about being green, it's about creating a stronger, more resilient economy.
It's about realizing that waste isn't inevitable, it's just bad design.
Well said. But we also have to remember this isn't just about companies and governments. Consumers have a part to play too.
Absolutely. What can everyday people do to support the shift to a circular economy?
A lot. Choose durable, repairable products. Look for companies that are prioritizing circularity. Repair and reuse things instead of throwing them away. And, of course, recycle and compost properly.
It's about making conscious choices as consumers, voting with our wallets.
Exactly. And remember those circularity scores we talked about. They could help people make those choices.
It all comes back to that, doesn't it? If people demand more circular products, companies will respond.
It's about creating a system where circularity is valued and rewarded at every level, from design to production to consumption.
So it's a bigger change than just switching up our economic system. It's a change in how we think.
Right. We need to shift away from this mindset of disposability and start thinking about how to use our resources wisely and responsibly.
It's a move towards stewardship, not just consumption. Well, this deep dive has been eye-opening. We've covered so much, from the nitty-gritty of measuring circularity to the broader implications for society and the economy.
It's definitely a complex issue, but a crucial one to address if we want a sustainable future.
Absolutely. And I think this new framework, with its focus on memory and how time affects circularity, gives us a powerful tool to help us make the right decisions.
It's a reminder that our choices have consequences that ripple far into the future, and that by thinking long-term and holistically, we can build a more sustainable world.
Thank you for joining us for this deep dive into the circular economy. We hope you've learned something new and feel inspired to help create a more sustainable future.
We hope so too. Until next time.
Welcome to the deep dive. Today we're going deep on a paper. It's called Circular Economy Design Through System Dynamics Modeling.
Oh, interesting.
Yeah, it really caught my eye.
Okay.
Because, circular economies, it's all about moving away from that wasteful, make, dispose, and making systems where resources are used for as long as possible.
It's a hot topic, for sure.
Absolutely.
And this research is really unique.
Yeah.
It uses concepts from physics and engineering to model circularity.
Wow.
It's not your typical sustainability paper.
It's not just about the feel-good ideas.
No.
It's applying real science to sustainability.
They actually introduced this idea, thermodynamical material networks.
Okay.
TMNs for short.
Okay.
Basically, they're networks of compartments that represent the stages in a material's life cycle. You can think of it like a map, like literally a map of where materials go and how they change, as they move through the economy.
So we're visualizing the whole system, raw materials to manufacturing to use, and then, end of life.
Absolutely.
But how do they actually measure circularity? Within this model?
So that's where it gets interesting. They use this metric for circularity. It's represented by the Greek letter lambda.
Okay.
And It's not just about, recycling rates or how much waste we make.
Yeah.
It's about the amount of unsustainable mass and flow in the whole system.
So like a holistic view.
Exactly.
View of circularity.
It considers things like getting virgin materials and the final disposal of things.
So the lower the lambda,
Yeah.
the more circular the system is.
Exactly. Yeah. A lower lambda means less material is lost from the system in unsustainable ways. And this is where the physics comes in. They use the first law of thermodynamics about energy conservation and Lagrange's equations of motion, which are usually used in physics to model like the movement of objects.
Right.
But here they are using it to track the materials in these networks.
Hold on. Lagrange's equations.
Yeah.
That sounds really...
It's intense.
For a sustainability paper. We're not talking about simple mass balances, right?
It goes much deeper than that.
Yeah.
They're really modeling the movement of materials through each compartment. So they were thinking about things like the mass of the material, the distance traveled, even the energy for transportation and transformation.
So they're treating each compartment like its own dynamic system, like with its own forces and...
Exactly. Yes. And by connecting these compartments together, they can create a model for the whole system. Cool. It's really powerful because it lets them measure how different design choices affect the circularity of the whole system.
I'm starting to see how this is interesting, but I'm a visual learner.
Okay.
Can we do a specific example? The paper mentions a linear case.
Right.
What's that?
So the linear case is that take, make, dispose model we are trying to get away from. So imagine a cube of material. It gets taken from a mine, transported by truck to a factory. Yeah. It's made into a product. Okay. The product is shipped to a store, someone buys it, and then, sadly, ends up in a landfill.
The classic linear journey.
Exactly. So they break down the cube's journey into compartments. So the mine, the truck, the factory, the ship, the store, consumer's house, the garbage truck, and finally the landfill. So each compartment is a node in their network. Right. And the cube moving between these is the flow of material.
So they're visualizing the life cycle of this cube as it goes through this system.
Exactly.
But how does this turn into calculating the lambda for this linear case? Okay,
so they give weights to each compartment based on like the mass of the material, the distance traveled, the type of process. Remember, lambda is all about minimizing that unsustainable mass and flow. So in this case, you've got the initial extraction from a non-renewable source, like from the mine, and then the disposal in the landfill. And both of those give a really high lambda score.
So the linear system gets a bad grade.
Yes.
Which isn't surprising. But that's just the...
that's the baseline.
Yeah, the baseline. What happens when we start adding in circular economy principles?
So they look at all kinds of scenarios where they tweak the linear system. So things like reducing material use, using renewable materials, even adding robotic repair. And we're going to see how those changes affect the lambda directly, which gives us insights into how to design more sustainable systems.
Okay, so we're about to see how even small changes can make a big difference in moving toward a circular economy. But can we go back for a second and talk more about Lagrange's equations?
Yeah, of course.
I'm still a little fuzzy on how they're actually applying those to the model.
It's super fascinating.
Yeah.
And worth taking a closer look at the math. So Lagrange's equations are all about how a system moves based on the difference between kinetic and potential energy.
Right.
Yeah.
I remember that from physics class.
Yeah.
Vaguely.
Yeah.
Can you refresh my memory on what those energy terms mean?
Okay. So kinetic energy is the energy of motion. So it's related to how fast something is moving in its mass. Like the heavier something is and the faster it's moving, the more kinetic energy it has. Potential energy is stored energy. It depends on an object's position or configuration. Like imagine a book above the ground. That's got potential energy because of gravity. If you drop it, that potential energy becomes kinetic energy as it falls. Okay,
that's starting to come back to me. But how do those apply to our cube in the circular economy? It's not like a...
It's not a falling book.
Falling book.
It's a bit more abstract here. So let's go back to that truck compartment.
Okay.
The cube's got a certain mass. The truck's moving at a speed. Those give us the kinetic energy of the system.
So the faster the trucks, the heavier the cube.
Yeah.
Higher kinetic energy. What about potential energy?
So that's where it gets a bit trickier. We are on a flat road, so we don't have that classic gravitational potential energy. But there are still potential energy terms to think about.
Like what?
Well, think about the forces on the cube.
Okay.
You've got the force from the truck's engine to move it forward.
Okay.
You've got friction between the tires and the road, which is resisting that motion, and maybe even air resistance as it moves.
So even though it's flat,
Yeah,
there's still a lot going on.
absolutely.
How do we account for that in the potential energy term?
So mathematically, we have to show each of those forces as a function of the cube's position. Like the force from the truck engine might be constant, but friction might be proportional to how fast the cube is moving.
So now we're getting into equations and variables.
Exactly.
And I'm guessing those equations
Really
could get
complex.
pretty messy.
And that's where Lagrange's equations come in. They're a systematic way to figure out the equations of motion, even if they are super complex.
So instead of trying to solve for all the forces
Yeah.
of motion directly, which could be a nightmare,
Exactly.
they're using Lagrange's equations as a
shortcut.
shortcut.
Exactly. So it's just a more elegant, efficient way
Okay.
to get those equations of motion.
So once you have the Lagrangian, which is kinetic minus potential energy, you can plug it in.
And they are a set of differential equations that relate the Lagrangian to the generalized coordinates of the system.
Generalized coordinates.
Yeah. They're just independent variables that describe the configuration of the system. In our case, it might just be where the cube is on the truck.
Okay.
Yeah.
So we're using the position of the cube as
Our variable.
variable to describe its motion.
And by plugging the Lagrangian into those equations, you can get an equation that describes how that position changes.
Okay.
And that's the equation of motion.
Wow.
It'll show how all those forces, the truck engine, the friction, air resistance, all that, affect the cube's movement.
This is pretty mind-blowing. I'm starting to see how these seemingly abstract mathematical concepts apply to real-world stuff, like designing a circular economy.
Yeah, it is pretty fascinating. And we just, scratched the surface here.
Yeah.
But the great thing about these Lagrange's equations is that they can be used on any system, no matter how complex. So from our cube, on the truck, all the way to a massive network of processes and material flows.
It's like having this tool that can help us understand and optimize these really complex systems in ways we never could before.
That's what makes it so exciting. It's changing how we think about sustainability, and it gives us the tools to make a difference.
This has been a really insightful look at circular economies.
Yeah.
We went from the basics all the way to how they're using physics and math to model these systems in a really new way.
Absolutely.
And I'm really curious to see how they apply these models to the scenarios you mentioned, the ones where they tweak the linear system to make it more circular.
Yeah. So that's what we are going to explore next. We'll look at how reducing material use, using renewable materials, and robotic repair, how all of that can change the lambda value and bring us closer to a truly circular economy.
I'm excited to see how that plays out.
Absolutely.
Stay tuned, listeners, because we're about to see how this research can help us design a more sustainable future. Welcome back to the Deep Dive. Before the break, we were talking about how researchers are using Lagrange's equations to model material flows in a circular economy.
Yeah, it's a pretty cool approach.
It is, but I'm really curious to see how these models are applied in real-world situations.
Absolutely.
You mentioned that they explore some specific examples of making the linear system, the take, make, dispose model more circular.
Yes, they look at a bunch of scenarios.
Okay.
And the results are really interesting. Should we jump into the first one?
Let's do it. What's the first tweak they make to that linear system?
So the first scenario looks at reducing material use. And they actually model two ways to do this. So in the first one, the manufacturer uses 50% renewable materials in their products. So instead of our cube being made entirely from, virgin materials, half of it now comes from a renewable source.
So that's looking at the source of the materials, making sure we're not just relying on
Yeah.
limited resources.
And then the second approach focuses on making the manufacturing process more efficient, so they use 20% less material overall.
Interesting.
So think of it as like our cube gets smaller, but still does the same job.
So both scenarios are about using less material, but in different ways.
Exactly.
I'm curious to see how those changes affect the lambda. Like, how much more circular does it become?
That's the $1 million question.
Right.
So remember, lambda is all about minimizing that unsustainable mass and flow.
Right.
So with the renewable materials, only half of the cube's mass is considered unsustainable when it comes to extraction.
Right, because the renewable portion isn't using up limited resources.
Yeah.
So how does that change the calculation?
Okay, so the paper uses this term unsustainable mass. It's shown by MUB, and it represents the total mass that makes a system not circular. So in the linear case, the whole cube is from non-renewable sources. So MUBIB is just 2 meter for extraction and M for disposal.
Right.
But with the 50% renewable materials, that initial extraction mass is cut in half. So the new MUB is M over 2 for extraction plus M for disposal. So MUB is 1.5 meter.
Okay, keeping up so far.
Good.
And lambda is calculated as the negative of this unsustainable mass, right?
Exactly. So instead of -2 meter, like in the linear case, we now have -1.5 meters, which is a big improvement.
Okay, so higher lambda, more circular.
Exactly.
Makes sense. What about that second scenario where they use 20% less material?
So in that case, our cube is smaller. So both the extraction and disposal use 80% of the original mass. So mud is 0.8 meters plus 0.8 meters, which comes out to 1.6 meters.
So the lambda there is -1.6 meters, still better than the linear case, but not as good as using the renewable materials. So it seems like where the materials come from has a bigger impact than just how much you use, at least in this example.
Yeah, I think that's a good observation.
Okay.
It really shows how important it is to look at the whole life cycle of a material and think about each stage.
So it's not enough to just use less. You have to think about where it came from
Absolutely.
in the first place.
Okay.
Okay, so we saw that reducing material use can boost circularity. What other tricks do they have?
So this is where things get really futuristic. They look at robotic repair as a way to extend the life of products.
Robotic repair.
Yeah.
Okay, now that sounds cool.
Yeah.
Are we talking about tiny robots disassembling and rebuilding our cube?
So imagine, instead of going straight to the landfill, the cube is sent to a special place, and robots take it apart, check the parts, and they might even fix or replace parts to make it last longer.
So it's like giving the cube a second life, maybe even more, before it has to be disposed of. I'm guessing this helps the lambda score a lot, right?
Absolutely. Adding repair really cuts down on stuff going to landfills, especially in shorter time frames. But this is where it gets a little more complex.
Right.
There's this idea of circularity memory.
Of circularity memory.
Yeah.
Now you've got my attention. What's that all about?
So it turns out that how long we measure circularity for can really change the results. The paper calls this, or 5.
Okay.
It's like repair is great in the short term because we're keeping things in use.
Right.
But if we look way into the future, everything breaks down eventually and needs to be thrown away.
Ah, so even with the best repair tech, we can't avoid...
You can't avoid it forever.
...the cube going to the landfill. How does that, how does circularity memory affect the lambda calculations?
So imagine we're comparing the linear system and the repair system over different times. If we start at the point where the cube would have gone to the landfill in the linear system, the repair system has a much higher lambda.
Okay.
It looks way more circular because, we haven't gotten to the point of disposal yet.
Right.
But if we look way into the future, both systems will end up with the same lambda because, well, both cubes end up in the landfill.
So the repair system is like, it's buying us time.
It is.
It keeps materials in use longer.
Yeah.
But it doesn't get rid of the fact that we need to dispose of things eventually.
That's right.
It challenges the idea of a perfectly circular system, right?
It definitely does. It reminds us that nothing is perfectly closed loop, Even with super innovative strategies, we have to think about the end of life for products and how to minimize the impact of that.
So it's not just delaying the inevitable.
Right.
It's making sure that when it happens,
Yeah.
it happens in the most responsible way.
Absolutely. Exactly. And this actually brings us back to those Lagrange's equations we were talking about earlier.
Okay.
Because by modeling the entire life of a product, including disposal,
Yeah.
we can really see its environmental impact
Right.
and see where we can make improvements.
Okay, I'm seeing how this all connects. We have the networks to visualize the system, lambda to measure circularity,
Yeah.
and Lagrange's equations to model how materials move through the system.
Exactly.
And by adding things like reduced material use,
Yeah.
renewable materials,
Right.
and robotic repair,
Right.
we can start moving that lambda in the right direction.
Absolutely. It's a multi-pronged approach that needs a deep understanding of both the physics and economics involved. And what's great about this research is that it gives us the framework to do just that.
This has been such a insightful look at how we can use science and engineering to design a better future. But before we wrap up this part,
Sure.
I want to go back to those Lagrange's equations and really unpack how they're being used in this model.
Okay, yeah, let's dive back into the math.
So we talked about how they're using Lagrange's equations to model the motion of our little cube as it's going through each compartment. And we touched on kinetic and potential energy.
Right.
Can we break down a specific example of how these equations are actually being used?
Yeah, absolutely. Let's go back to that truck compartment example.
Okay.
So picture our cube on a flatbed truck just cruising along at a constant speed.
Okay, I'm picturing it.
Yeah.
Nice straight road truck moving
Yeah.
along. What happens next?
Okay, so to use Lagrange's equations, we got to define what's called the Lagrangian of the system. It's
Right.
just the difference between kinetic energy, which is T,
Okay.
and potential energy, V.
Okay, so L equals T minus V.
Yeah.
Got it. What are the kinetic and potential energies in this case?
So the kinetic energy is easy. It's just the energy from the cube moving. Since the truck's going at a constant speed, we can use the regular formula. 1/2 times m times v squared, where m is the mass and v is the velocity.
So the heavier the cube or the faster the truck, the higher the kinetic energy.
Exactly.
Got it.
Yeah.
What about potential energy?
Okay, so potential energy is trickier here.
Yeah.
We're on a flat road, so there's no regular gravitational potential energy.
Right.
Like there would be if we were lifting the cube. But we still got to think about potential energy.
Look, what else would affect potential energy on a flatbed truck?
Well, you have to think about the forces acting on the cube. So there's the force from the truck's engine moving it forward. There's friction from the tires on the road.
Right.
And maybe even air resistance pushing back on the cube.
So even though we're on a flat surface, there's still a lot going on in terms of
Lots of forces.
forces and energy. How do we account for that in the potential energy term?
Okay, so this is where the math gets a bit more complex. We have to represent each of those forces as a function of the cube's position.
Okay.
So the force from the truck might be a constant, but friction might change depending on how fast the cube's moving.
So we're getting into some serious equations and variables here. And those equations can get pretty messy depending on the forces involved.
Yeah, they can get pretty complex.
Right.
That's why Lagrange's equations are so useful. They give us a way to get those equations of motion even when they're super complex.
So instead of trying to figure out all the forces in motion directly, which could be a nightmare,
Yeah, a nightmare.
they're using Lagrange's equations as
Shortcut.
Yeah,
Shortcut.
yeah.
Lagrange's equations are just a more elegant way to find those equations of motion.
Okay.
So once we have the Lagrangian
Yeah.
kinetic minus potential energy, we plug it into Lagrange's equations, which are differential equations.
Okay.
These equations show how the Lagrangian changes depending on the generalized coordinates of the system.
Generalized coordinates. What are those?
They're just independent variables that describe how the system is set up. In our case, it's just the position of the cube on the truck.
Okay, so we are using the position of the cube as our variable to describe how it's moving.
And by plugging the Lagrangian into those equations, we can figure out how that position changes over time.
Okay.
That's the equation of motion. And it'll show how all those forces, the truck engine, friction, air resistance, affect the cube as it moves.
This is pretty mind-blowing. I'm really starting to see how these kind of abstract math ideas can be used to solve real-world problems.
Exactly.
Like designing a circular economy.
It's really cool.
Yeah.
And we've just, barely scratched the surface here.
Right.
The cool thing about Lagrange's equations is They can be used on systems of any complexity. So from our simple cube to a huge network of processes and materials.
So it's like having this really powerful mathematical
Yeah.
tool
Yes.
to help us understand and make these complex systems better
Absolutely. That's exactly it.
in ways that we couldn't before.
And that's what makes this research so exciting. It's really changing how we think about sustainability and gives us tools to actually make things better.
This has been such a fascinating look at circular economies.
Yes.
We went from the basics to how they're using physics and math
Yeah.
to model these systems in a really new way.
Absolutely.
But I think it's time for a break.
Okay, yeah. Let's take a break and then come back to see how Lagrange's equations play out when we try to make the linear system more circular.
Stay tuned, listeners. We'll be right back to continue our journey into the world of circular economy design. Welcome back to the deep dive. Before the break, we were looking at how researchers are using Lagrange's equations to model material flows in a circular economy.
It's a really powerful approach.
I'm still kind of wrapping my head around it all.
It's pretty complex stuff.
But I'm starting to see the potential. Before the break, we were about to talk about how these equations play out when we try to, tweak that linear system to make it more circular.
Right. So let's go back to those scenarios. The first one was using 50% renewable materials,
Okay.
and the second was reducing material use by 20%.
Right. And we saw that those changes led to a lower unsustainable mass
Yeah.
and a higher lambda, meaning a more circular system. But how do those changes actually affect the Lagrange's equations?
So that's where it gets really interesting. Let's look at the scenario with the 50% renewable materials. Remember, Lagrange's equations use the difference between kinetic and potential energy. The kinetic energy, which is about the mass and velocity of the cube, would stay the same.
Because we're not changing the size of the cube
Exactly.
or how fast it's moving.
The change happens in the potential energy term.
Okay.
Remember, we talked about potential energy being affected by things like the force of the truck engine, friction, the angle of the road, all that.
Yeah, it was all those forces on the cube.
Right. So now we have to think about the fact that half of the cube comes from a renewable source. This means the energy needed to extract that material is probably different from the energy needed for non-renewable materials.
So it's not just about the mass of the cube anymore.
No.
We're also thinking about the energy that goes into the materials themselves.
Exactly. That embedded energy is part of the potential energy in Lagrange's equation. So, for example, if the renewable material is local and doesn't need a lot of processing, the potential energy for extraction would be lower compared to something mined and transported over long distances.
Okay, so the potential energy in Lagrange's equation is showing not just the physical forces on a cube,
Right.
but also the energy in the materials themselves. That's really interesting.
It is, and it shows how these equations can capture a much bigger picture of sustainability.
Right.
It's not just using less stuff, it's also about the energy and resources needed to make and transport that stuff.
So like moving past a simple mass-based analysis
Yeah.
and also looking at energy.
Exactly.
What about the second scenario, where they reduce the overall material use by 20%?
Okay, so in that case, the change would affect both the kinetic and potential energy. A smaller cube would have less mass, which would change the kinetic energy, especially when the cube's being moved around.
Right, less mass, less energy to move it.
Exactly. And the potential energy would change too, because the forces acting on a smaller cube are different. Like friction would be less because there's less surface area touching things.
So it's like a domino effect. Changing the cube's size affects all the forces and energy in each stage.
You got it. And that's what Lagrange's equations let us do. Model all those changes and see how even small tweaks can affect the whole system.
Okay, so we've seen how reducing material use can change those Lagrange's equations and make the system more circular. But what about that robotic repair scenario?
Ah, yes. Robotic repair adds a whole new layer to the model.
Right, it's not just a straight line from extraction to disposal anymore.
Exactly. It creates a loop, so instead of going to the landfill, the cube gets another chance, maybe several, through repair and reuse.
Right, and that loop really changes those equations, right?
Yeah, it does. Remember that idea of circularity memory and how the time frame we look at can change how circular things seem?
Yeah, it was that idea that repair looks good in the short term, but if we look way ahead everything breaks down eventually.
Right. And Lagrange's equations can help us model that change over time. By adding that repair loop, we're basically creating a whole new set of compartments and flows in the equations.
So it's like adding new variables and equations to the model,
Yeah.
each one representing a different part of the repair process. What would those equations look like?
So they would include things like the energy to transport the cube to the repair facility, the energy the robots use for disassembly and repair, even the energy in any replacement parts.
So we're accounting for all the energy used in that repair loop.
Yeah.
How does that affect the overall lambda?
So that's where it gets interesting. By adding a repair loop, we're basically reducing how much stuff goes to the landfill, at least for a while. This means the unsustainable mass, MUB, is lower, which gives us a higher lambda.
Okay, so the repair loop is giving us more time
It is.
and making the system seem more circular in the short term.
Right.
But what about in the long term when everything eventually breaks down?
That's where circularity memory comes in. Lagrange's equations let us model the system over different time frames. We can see how lambda changes as we look further into the future. And eventually, the lambda for the repair system starts to look like the lambda for the linear system.
Because no matter how many times we repair it, the cube will eventually just be too broken or too expensive to repair.
Exactly. That's a really important point that those equations can show us. It reminds us that even with cool new technologies, we need to be realistic about the limits of circularity and design systems that are sustainable throughout a product's whole life.
This is really making me think differently about circularity. It's not just about keeping things in use forever, it's about making the system as environmentally friendly as possible over the long term.
I think that's a great way to put it. And that's what's so great about this research. It gives us a way to think about circularity more carefully, considering materials, energy use, and even how time plays a role.
It's been amazing exploring how these researchers are using physics and math to help us design a circular economy. But as we wrap up, I'm wondering, what are some of the limitations of this approach?
That's a great question. Like any model, these equations have limitations. First, they need good data. To model all the forces, energy, and materials accurately, we need data on things like material properties, manufacturing processes, transportation distances, even how people behave.
So bad data in, bad results out.
Exactly. And getting good data can be hard, especially with complex supply chains that go across many countries.
Right.
Another thing is, these models are simplified versions of reality. They can't capture every single detail of a system.
It's like trying to make a map of a city. You can show the main streets, but not every building and path.
Exactly. So we have to be aware of the assumptions we're making and realize that the model might be oversimplified.
So it's about finding a balance
It is.
between making the model complex enough to be accurate, but simple enough to actually use and understand.
Absolutely. And we can't forget about people. These models are just tools. We need experts who understand the science and the real world to use the results and make good decisions.
So it's not just about the math, it's also about the people using the models to guide policies and design choices. It's a good reminder that even with all this data and technology, human judgment is still important.
I completely agree. The best solutions come from combining scientific knowledge with human ingenuity.
Well said. This has been an incredible deep dive into circular economies, exploring both the possibilities and the challenges. As we wrap up, I'm feeling both hopeful that we have the tools to design a better future
Yeah.
and realistic about the work we still need to do.
I agree. The path to a truly circular economy is long and complicated, but I'm confident we're heading in the right direction.
Thanks for joining us on this deep dive, listeners. We hope you've enjoyed it. Until next time, keep exploring, keep asking questions, and keep pushing the limits of what's possible. All right, let's dive into something really cool today. We're looking at a paper about using system dynamics modeling to design a circular economy. Sounds a bit dense, I know, but stick with me. This one is packed with some interesting ideas.
What really stood out to me was how they connect circularity with, fundamental principles in physics, thermodynamics even.
Yeah, you don't see that every day in a paper about sustainability. But
Yeah.
okay, let's back up a sec. The paper kicks off talking about our current linear economy, the whole take, make, dispose model.
Right, and they don't sugarcoat it. They're like, straight up, this linear approach, not sustainable. We're going to run out of resources and end up buried in trash, basically. It's like heading straight for an ecological cliff.
Yikes. Okay, so Problem laid out pretty clearly. Then they bring in circularity as a possible solution, right? So instead of a one-way street for materials, we try to create loops. Keep those materials in use for as long as possible.
Exactly. They talk about those familiar R's: reduce, reuse, repair, remanufacture. But they don't just list them out. They try to actually quantify circularity.
Which is where the math comes in. They introduce this concept of lambda. It's represented by the Greek letter, and it measures the unsustainable mass flows, the stuff going into landfills or leaking into the environment.
Right, and they actually define lambda like this: mub plus os.
Whoa, okay, break that down for me.
So mub is the unsustainable mass that's transported in like batches, represents the unsustainable flow, and O stands for a time interval.
Okay, so we've got this equation. Then the paper goes into these examples, right? They start with a classic linear take, make, dispose scenario, the linear case.
And to illustrate it, they use this visual representation, a geometric digraph. Circles are like different compartments: the mine, the manufacturer, the user, and finally the landfill. Arrows show how the materials move between them.
Got it. So in this linear case, it's just a simple one-way flow. Materials extracted from the mine, sent to the manufacturer, then to the user, and boom, straight to the landfill. No attempt at recovering or reusing anything.
Exactly. No loops, just a straight line to the landfill. And when they calculate lambda for this system, they get a value of matic to meters, meaning twice the mass of the material extracted ends up as unsustainable flow.
Which makes sense, right? You've got AMBA being extracted and then another being tossed out. Both are contributing to those unsustainable flows.
Precisely. And that's where they start looking at how different design choices can bump up the circularity, basically make that lambda value less negative. They introduce this concept of reducing.
Right, the idea of simply using less material in the first place. And they've got two scenarios for this reducing case. The first one involves the manufacturer deciding to use 50% renewable materials for their product.
Yeah, they give an example of using 50% bioplastic, alongside the traditional synthetic plastic. So only half the original mass, like M2, needs to come from that non-renewable source. But the whole product, that full still ends up in the landfill.
Because even though it's bioplastic, it's not like it magically disappears, right? It's still often not biodegradable or easily recyclable.
Exactly. It might be from a renewable source, but the product as a whole not really designed for circularity. And the lambda for this scenario, they call it core 1, it comes out to be -1.5 meters.
So an improvement from that -2 meter of the straight-up linear case. Still not ideal, though. And this shows that just swapping materials, even for renewable ones, isn't a magic bullet for circularity.
Right. It's not just about the material itself, it's the whole design. Now, that second reducing scenario is all about using less material overall, whatever that material is. They use the example of a manufacturer who figures out how to make the same product, but with only 80% of the original material.
So basically cutting out waste from the get-go. Less going in means less going out. Makes sense.
Yeah, so in this case, you have 0.8 meters extracted from the reservoir and another 0.8 meter ending up in the landfill, adding up to 1 at 1.6 meters for the lambda R2.
Huh. That's actually a smidge better than the bioplastic scenario. Interesting. It really highlights that just using less, even without switching to fancy renewables, can have a big impact.
Yeah, that reduction at the source, it's a powerful tool for minimizing environmental impact. And it goes way beyond manufacturing. Think about your own consumption habits.
It really makes you think. Okay, so we've seen how reducing material use can make that lambda value look better. What's next in their exploration of circularity?
Well, they move on to a more, I guess you could say, advanced scenario, the case of robotic repair. Imagine products, instead of being trashed, being sent to a place where robots repair them. They get a second life.
Okay, now we're talking. Robots fixing stuff sounds futuristic and efficient. But I'm curious, how does this repair step actually affect that lambda value?
That's where this idea of circularity's memory comes in. In the short term, a robotic repair really cuts down that unsustainable flow. The product doesn't immediately become landfill waste.
But eventually, even a repaired thing is going to reach the end of its life. Wouldn't the lambda for this robotic repair scenario end up being the same as the linear case, that magnitude meter?
That's the thing. If we're looking at lambda over a super long time, yeah, the repaired product will eventually become part of the unsustainable flow. So technically, the lambda's up still -2 meter.
So back to square one. Wait, hold on. I remember something about a time horizon being factored into the lambda equation. What was that all about?
Right. That's where they bring in lambdify, which takes into account a specific time horizon, represented by the Greek letter phi. Instead of just the ultimate fate, we can assess circularity over specific time frames.
Ah, okay. We're basically zooming in on a particular period, and that allows us to see the good that robotic repair does, even if the product does eventually bite the dust.
Yeah, exactly. Let's say in that basic linear case, a product hits the landfill at time T5I. If we set our food to be T50, then lambda phi for the linear case would still be that -2 meter, but for the robotic repair case, it would be bumped because only the initial extraction is happening in that time frame. The repaired product is still chugging along.
Okay, so by picking a relevant time horizon, we're highlighting the benefit of stretching out the product's life. It's like we're shifting from a snapshot to a time lapse, seeing the effects of our choices unfold over time.
Great analogy. And the paper really stresses this. Circularity is about both closing the loop and expanding it. Keep those materials going round and round for as long as possible.
Got it. So lambda phi adds a whole other level of complexity, but it gives us a more realistic view of circularity, not just the end, but the whole journey.
Precisely. And that's where things get really interesting, because then the paper goes on to link this whole circularity idea to, get this, physics.
Hold up, physics. Thought we were deep in economics and sustainability. How does physics even enter the picture?
That's what's so cool about this paper. It brings together these different fields. They actually use analytical mechanics to model the way materials move through a system.
Analytical mechanics, now you're testing my college physics knowledge.
Think back to Lagrange's equation. Remember that. It describes the motion of a system based on energy principles. The authors actually show how that equation can be derived from the first law of thermodynamics.
Okay, so they're saying the flow of materials in a circular economy, it can be analyzed using the same ideas that govern how energy behaves in a thermodynamic system.
Exactly. And this allows them to calculate stuff like the position and velocity of a product as it hops between those compartments. Pretty hardcore, huh?
Wow, we're going deep now.
Yeah.
So they're basically using physics to prove that a circular economy works.
I wouldn't say prove in the strict mathematical sense, but they're building a solid theoretical base for circularity, grounded in well-established science. And that's a big deal.
Okay, starting to see the connections here. They use this physics-based approach to model all those scenarios we talked about. The linear case, the reduction scenarios, the robotic repair. What do they find?
Well, they really drive home the point that both the type of material and the time horizon matter a lot when you're assessing circularity. They also emphasize that it's not just about optimizing one little thing, it's about designing whole systems for circularity.
It's that systems thinking, right?
Yeah.
Looking at the whole web of connections and the long-term effects.
You got it. And this is where the paper goes beyond those theoretical models and into real-world stuff. How do their findings apply to design and policy decisions? But I think that's a conversation for the next part of our deep dive.
Oh, you've got me hooked. This paper is really pushing the boundaries of how we think about sustainability. Can't wait to see what's next. Let's give our listeners a minute to digest all this. It's complex stuff, but super fascinating.
So jumping back in, the paper gets into something that's often kind of overlooked when we talk about circularity, the energy it takes to keep those materials moving in those loops.
Yeah, it makes sense if you think about it. Even with robots doing repairs, you got to power the robots, transport the stuff, all that. It seems like there could be a trade-off, more circularity, but also maybe more energy use.
That's a major point they bring up later in the paper. They're honest. They say, hey, we focused on mass flows, but a complete picture needs to include the energy side of things too.
Right. You could have a system that looks super circular if you're just looking at materials. But if it takes tons of energy to maintain, is it really sustainable in the long run?
Exactly. Imagine a product designed to be repaired over and over. Great for extending its life, less waste. But each repair probably uses energy, taking it apart, replacing parts, putting it back together.
And that energy comes from somewhere. Fossil fuels, renewables, whatever the mix. There's an environmental cost to producing it.
Right. You got to factor that cost into the equation when you're talking about sustainability. They point out that we need more research to get a framework that looks at both mass and energy flows.
So like a circularity dashboard, multiple gauges, one for material circularity, another for energy efficiency, maybe even more for water use, emissions, all that.
Great visual. And it highlights how complicated it is to design truly sustainable systems. You can't just zoom in on one thing. It's about how everything interacts.
And that's where trade-offs get important, right? Sometimes going all in on one goal might mean compromising somewhere else.
Totally. A balancing act. Like, using recycled materials is great for material circularity, less need for virgin stuff. But recycling itself takes energy, right? Might offset some of those gains.
Okay, so it's finding that sweet spot. Max circularity, minimal bad stuff elsewhere. But how do you even find that balance? It's got to be a super complicated problem to solve.
Complex for sure, but they have some ideas about how to approach it. They talk about multi-objective optimization, where you can look at a bunch of goals at the same time.
So instead of just trying to shrink that lambda value for material circularity, you could also aim for, say, low energy use, low emissions all at once.
Yeah, and there are algorithms, fancy math stuff, that help explore different designs to find the ones that do well on all those goals at the same time. Like a compromise, but the best kind.
Okay, one approach. Anything else they suggest for handling the energy challenge?
They really emphasize the importance of thinking about the whole life cycle, cradle to grave, from the raw materials all the way to what happens when it's no longer useful, and design for energy efficiency at each stage.
So not just tweaking one little process here or there, it's a big picture thing, being smart about energy every step of the way.
Exactly. Like when you're designing, maybe pick materials that are less energy intensive to process. During manufacturing, make sure the process isn't wasting energy. And when it's at the end of its life, design it so it's easy to take apart and reuse parts. Saves energy on recycling or disposal.
It's like circularity within circularity. Each stage connected, and each stage a chance to be energy smart. I'm kind of getting overwhelmed, though. There's so much to consider.
I know, it's a lot, but the authors are really pushing the limits of how we think about this stuff. It's not going to be easy, but they're showing us just how complex the challenge is and getting us to think deeper.
And as complex as it is, it's kind of exciting too, right? It feels like a paradigm shift, leaving behind those old linear ways and realizing that everything is connected.
Definitely. This paper shows the power of combining different ways of thinking. Economics, sustainability, even physics, they're helping us figure out how to get to a more sustainable future.
Okay, so energy and circularity. Any other big takeaways they bring up as we wrap up our look at this paper?
They do mention a couple more important things. One is about needing a better, more specific definition of circularity itself. They admit their current lambda metric, it's helpful, but has some limitations.
Oh, like what?
Well, it treats all materials as the same, but in the real world, some are more abundant or have less environmental impact than others. Using a kilogram of recycled aluminum is way better than using a kilogram of newly mined aluminum, right?
Yeah, so just measuring the mass doesn't tell the whole story.
Yeah.
We need a way to tell the difference between different materials and take into account their specific characteristics.
Exactly. They suggest coming up with a weighted definition. So different materials get different weights based on their environmental impact.
Like a ranking system. Most sustainable at the top, least sustainable at the bottom. And then your circularity score reflects not just the amount, but the quality of the material being kept in circulation.
Yep. And you could even refine it further, include things like how far the materials have to travel, how much energy it takes to process them, even the social impact of where and how they're extracted or made.
Wow, a truly comprehensive metric. A big challenge to create, but so important if we want to make smart decisions about designing circular systems.
Couldn't agree more. And they stress that getting to circularity will take everyone working together. Researchers, policymakers, businesses, even individuals.
A circular economy dream team. Everyone bringing their skills to the table. Engineers working with environmental scientists, economists, maybe even psychologists, all focused on creating a truly sustainable future.
Now that's a vision. And I think it's possible. This paper makes me hopeful that we can ditch that old take, make, dispose model and build a world where materials are constantly flowing in loops. Less waste, more efficient use of resources.
I'm feeling inspired. This deep dive has really opened my eyes to how complex, yet also how full of potential this whole circularity thing is. My brain's a little fried though, huh?
Understandable. Lots to take in, but sometimes the tough stuff is the most rewarding to grapple with.
So true. This paper has definitely pushed me to think bigger, beyond simple solutions. Everything is connected. And I bet our listeners are feeling that too.
I hope they're also feeling fired up, because at the end of the day, we want this deep dive to not just inform, but empower people. You can be a part of building a more circular future.
Absolutely. Start by asking yourself, what am I buying? What choices am I making? What systems am I part of? Every little bit counts.
Well put. But before we let our listeners go off and contemplate the future of circularity, there's one more crucial point they make. It goes back to the very heart of designing a circular economy, the idea of taking inspiration from nature itself.
Oh, that's interesting. Nature's been doing circularity for billions of years. What can we learn from those natural processes? This feels like the perfect way to transition to the final part of our deep dive. So we've covered a lot of ground, the math, the physics, the energy stuff, even needing a better definition of circularity. But you mentioned natural systems. How do they fit into all of this?
Well, the paper brings up a really important idea that sometimes gets lost in the technical details. A circular economy should be trying to copy the kind of circularity we see in nature.
Right, that makes sense. Natural ecosystems, they've been operating in these closed loops for, well, forever. Materials constantly cycling, getting reused. There's no such thing as waste in nature. Everything is a resource.
Exactly. And the authors are like, hey, we can learn a ton from nature as we design our own circular systems. They even talk about this thing called industrial ecology, which basically takes inspiration from ecosystems to create more sustainable industrial processes.
So it's about changing how we think, right? Moving from that linear take, make, dispose to a way of thinking that's more cyclical, more interconnected, like an ecosystem where everything is linked. But how do we actually put those natural principles into practice when we design stuff?
Now that's where it gets really cool. They give a few specific examples of how to mimic nature in the context of circularity. One example is biomimicry, which is basically copying the forms, processes, or systems we see in nature.
Okay, like looking to nature for design ideas. What are some examples?
Well, think about wind turbine blades. Some engineers are using the shape of whale fins for inspiration. Whale fins are incredibly efficient at moving through water. Mimicking those shapes can make wind turbines more efficient, producing more energy with less material.
Wow, that's amazing. So it's not about literally copying nature, but more about understanding the principles behind it and applying them creatively.
Precisely. Another example they talk about is closed-loop manufacturing, industrial processes that are designed to minimize waste and recover as many resources as possible, just like an ecosystem.
So creating a little mini ecosystem within a factory where the byproducts of one process become the ingredients for another. Are there real-world examples of this?
Oh yeah, definitely. They mentioned the Kalundborg symbiosis, an industrial park in Denmark. A bunch of companies there work together, sharing and reusing resources. What would be waste for one becomes a valuable input for another, like excess heat from a power plant. It gets used to heat nearby homes and businesses. And wastewater from an oil refinery, it's treated and used to irrigate crops.
That's incredible. It's like a truly integrated and interconnected system, just like a natural ecosystem. Really shows the potential for collaboration and ingenuity to make circularity a reality.
It does. And the authors point out these are just a couple of examples. There's so much more we can learn from nature. As we keep exploring, we're bound to discover even more innovative and sustainable solutions.
This is super inspiring. It feels like we're right on the edge of a huge shift in how we design and interact with the world. Moving away from those old linear extractive models towards something more circular, more interconnected, more in line with how nature works.
I'm with you. This paper, while complex and challenging, paints a hopeful picture. A future where human systems and natural systems work together, creating a world that's more sustainable and resilient for everyone.
Well said. This deep dive has been quite a journey. From the basics of circularity all the way to some pretty mind-bending ideas. We've tackled equations, philosophical questions, even dipped our toes into biomimicry.
It's been a fascinating exploration. I hope our listeners are walking away with a better understanding of just how intricate, how promising, and how urgent this whole transition to a circular economy really is.
I think they are. And as we wrap up, there's one last quote from the paper that really stuck with me. They say, "Circularity is not just a destination. It's a journey of continuous improvement."
Love that. It's a good reminder that building a circular economy isn't about getting everything perfect right away. It's about constantly learning, adapting, and always striving to do better. It's a journey we're all on together.
Absolutely. So to our listeners, keep exploring, keep asking questions, keep pushing for a more circular future. Every step we take, every choice we make can make a difference.
And remember, nature's wisdom is all around us. If we pay attention, learn from those natural processes, I think we can unlock the secrets to creating an economy that's not just circular, but truly regenerative.
Until next time, keep those minds curious and those actions circular. All right, let's dive into another deep dive. This time we're tackling a paper that uses some pretty serious math to talk about circular economy design.
Yeah, it is. It's a paper that definitely needs a deep dive.
Using system dynamics modeling, to be exact.
Yeah.
I'm already intrigued and a little intimidated, but luckily, we've got our expert here to guide us through it.
It's definitely a dense paper, but the way it uses math to like actually model circularity, it's really interesting.
So before we get too lost in the equations, can you just remind us what a circular economy is and how it's different from the way we do things now?
Yeah, absolutely. So a circular economy, it's all about moving away from this traditional like linear model of take, make, dispose, and shifting towards a system where resources are constantly being reused and repurposed, kind of mimicking nature's cycles.
So it's not just about recycling, it's about redesigning the entire system.
Exactly.
With sustainability in mind.
Precisely. And this paper provides a framework for like optimizing that system using mathematical models.
So it's taking something that can feel really conceptual, fuzzy,
and giving us a concrete way to approach it.
Exactly.
And it specifically delves into system dynamics modeling, which allows us to understand how materials flow within a system over time.
I feel like I've come across systems dynamics models before.
Yeah.
In other contexts, are they similar?
They are similar in that they're aiming to represent these complex systems and their interactions, but in this paper, they're specifically applying it to the flow of materials in an economy.
Okay, got it.
Yeah.
So how does this paper approach that, like the challenge of modeling something as complex as, material flow?
So they start with this concept of compartmental modeling. Think of it like breaking down a complex machine like a steam engine into its individual parts or compartments, you know?
So like analyzing how those parts interact and contribute to the overall functioning of the engine.
Exactly. And in this case, the engine is the flow of materials in an economy. The compartments could represent things like raw material extraction, manufacturing, product use, recycling, and even disposal.
Okay, so we are essentially creating a map of how materials move through the system.
Yeah. Exactly.
But how does that map then help us achieve circularity?
That's where the math comes in. So once we've defined our compartments, we can use these like mathematical equations to model the flow of materials between them.
Right. And that's where I saw this term thermodynamic material networks, or TMNs. Come into play. Is that right?
Yeah. So TMNs are a way to represent those compartmentalized systems mathematically.
Okay.
Picture like a network of nodes and arcs where the nodes represent the compartments and the arcs represent the flow of materials between them.
So it's kind of like a visual representation of the mathematical relationship that governs the flow of materials.
Precisely. And the beauty of this approach is that it allows us to quantify something that's often really hard to define, which is circularity.
Yeah, circularity as a concept just seems so broad.
Right.
So how does this paper define it and then measure it?
So they define circularity, which they denote with the Greek letter lambda, as a function of what they call unsustainable mass.
Okay.
So essentially, the goal is to minimize the amount of unsustainable mass in the system.
Okay. What do they mean by unsustainable mass, though?
Yeah, so unsustainable mass refers to any material that is either extracted from like non-renewable sources or ends up as waste in landfills, incinerators, polluting the environment.
Okay, so the more unsustainable mass a system has, the lower its circularity score.
Precisely.
And the more we can minimize that unsustainable mass, the more circular it becomes.
Exactly.
And the higher the score.
Yeah.
So we are trying to find the optimal configuration of those compartments and flows to achieve the highest level of circularity, right?
Yeah.
So it sounds like we're talking about an optimization problem.
It is, yeah.
Like finding the best possible arrangement to maximize circularity.
You got it. And they actually mathematically frame it as N, representing the ideal circular network, equals the argument that maximizes lambda N.
Okay, so it's not just about describing how things move. It's about figuring out the most circular way to make them move.
Exactly.
And to do that, they turn to a pretty powerful tool from analytical mechanics, which is Lagrange's equation of motion.
Right.
That sounds like some serious physics.
It is, but bear with me.
Okay.
The key takeaway is that Lagrange's equation, which is typically used to describe the motion of physical objects, can also be applied to model the flow of materials.
Okay.
They actually even provide a proof in the paper demonstrating that this application is consistent with the first law of thermodynamics.
Okay, I'm starting to see how these pieces fit together.
Yeah.
But why is it important to bring in Lagrange's equation? Like, what does it add to our understanding of circularity?
So it provides this powerful framework to model the dynamics of material flow in each compartment.
Okay.
Taking into account things like energy and forces and resistances.
So we are moving beyond a static map to more of a
to a dynamic model where things are constantly in motion.
Right.
And that dynamic perspective is crucial for accurately calculating circularity, especially when we start considering things like time horizons and the impact of different circularity strategies.
Okay, this is all starting to make sense, but how do they actually put this into practice? Like, do they use real-world examples?
They do, yeah. The paper presents several examples to illustrate this approach, and the first one they use is a classic linear system, which is that take, make, dispose model that we talked about earlier.
Okay, so like a very non-circular example to start with.
Yeah, it's like our baseline.
Okay.
And they model the journey of a single unit of material, let's just say it's a cube, as it travels from a non-renewable resource through manufacturing, shipping, use, and ultimately disposal in a landfill.
And I'm assuming they use Lagrange's equation to model the movement of that cube at each stage.
You're right, yeah.
Right.
They take into account things like the, friction and the force required to transport it, and even the slope of the road leading up to the landfill.
Oh.
It's very detailed.
So what does that simple example tell us about circularity? I'm guessing it doesn't score very high?
No, you guessed right. The linear system has a very low circularity score because, of course, all that material extracted from that non-renewable source ends up as waste in the landfill.
So the unsustainable mass is essentially just that cube at the beginning and that cube at the end.
Exactly.
Well,
But the real power of this modeling approach comes when we start comparing different circularity strategies.
right. So that linear example just sets the stage for exploring more sustainable approaches.
Precisely. And the next examples in the paper focus on reducing material demand and introducing repair cycles as strategies to improve circularity.
Ooh, I'm eager to see how those strategies play out in the model and how they impact that circularity score.
Yeah, and that's exactly what we'll delve into next.
Welcome back to our deep dive into circular economy design. So we've laid the groundwork. We understand how the paper uses system dynamics modeling and Lagrange's equation to quantify circularity. Now, I'm really curious to see how those equations come to life when we start analyzing specific strategies.
Yes, let's get into the equations and see how they reflect these changes in material flow and ultimately circularity.
Okay.
So we left off talking about the linear system example,
Right.
which served as our baseline with its pretty dismal circularity score.
Right, because all of that material ended up in the landfill.
Right.
It highlighted the need for more sustainable approaches. And the next example in the paper focuses on reducing material demand, right?
Exactly. And they explore two scenarios within this example. The first one involves incorporating renewable materials into the production process.
Okay.
So imagine, for instance, that the manufacturer starts using 50% bio-based plastic instead of relying solely on traditional, non-renewable plastic.
Okay, so we're essentially reducing the amount of material that's extracted from non-renewable sources.
Right.
How does that impact the equations in the circularity score?
So remember that circularity, represented by lambda, is based on unsustainable mass.
Yeah.
And by using renewable materials, we've effectively cut the unsustainable mass derived from non-renewable sources in half.
Okay, so instead of having the unsustainable mass be 2 meters for the non-renewable source and M for the landfill, it's now M2 for the extraction plus M for the landfill.
Right, and this change is reflected in the calculation for lambda, which now becomes 1.5 meters,
Okay.
as shown in equation 19.
Which is a significant improvement
Yeah.
compared to the negative meter that we saw in the linear case.
Exactly. It highlights the power of, incorporating renewable resources into our production systems.
Yeah, it shows that even a partial shift towards renewable materials can make a big difference.
Absolutely.
That's pretty cool.
Yeah.
The second scenario in this example explores reducing just the overall amount of material needed to make the product. So it's like designing for efficiency, right?
Exactly. Imagine the manufacturer discovers a way to, achieve the same functionality with only 80% of the original material. This reduction directly translates to less material being extracted and less waste ending up in the landfill.
Okay, so both the mass extracted from the non-renewable reservoir and the mass ending up in the landfill would be reduced to like 0.8 meters?
Precisely.
Okay.
The total unsustainable mass now becomes 1.6 meters, leading to a circularity score, lambda, of minus 1.6 meter, as shown in equation 20.
Still a noticeable improvement over the linear case, even though we didn't introduce any fancy new materials.
Right.
It really underscores the importance of designing for efficiency right from the start.
You got it.
Cool.
Reducing material consumption, whether it's through renewable sources or just using less overall, plays a key role in improving circularity.
I think it's really interesting how these seemingly simple changes in material use have this really quantifiable impact on the circularity. It's like we're getting a clear picture of how effective different strategies can be.
Indeed, the equations provide that concrete way to assess and compare the impact of these different approaches.
Absolutely.
Now let's move on to example 3, which introduces a completely different strategy. Robotic repair.
Oh yeah, robotic repair. That was when I was reading through the paper, I was kind of surprised that incorporating a repair stage didn't automatically lead to a better circularity score.
It is kind of counterintuitive, isn't it?
Yeah.
So while repair intuitively seems like it should improve circularity, the initial calculation, which just considers the amount of material that eventually ends up in the landfill, it doesn't immediately reflect this improvement.
Right, because even with repair, that material still eventually reaches the landfill.
Yeah.
So why bother with repair at all if it's not actually improving the circularity score?
That's where the concept of circularity memory comes in.
Okay.
And it highlights the importance of the time horizon over which we are evaluating circularity. So while the material might still end up in the landfill, it takes a lot longer to get there with repair.
So it's not just about the final destination of the material, it's also about the journey.
Exactly.
And the time it spends in the system.
Yeah.
Repair extends that journey and delays the ultimate disposal.
Exactly. If we're only looking at a short time horizon,
Yeah.
the repair stage might not make much of a difference, but when we consider a longer time horizon,
Right.
the benefit of extending the product's lifespan through repair becomes much more clear.
So it's like comparing a sprinter who runs a short distance really fast and then stops
Yeah,
to a marathon runner who keeps going for a much longer time.
right.
Both eventually reach the finish line, but the marathon runner covers a much greater distance.
That's a great analogy.
And just like with the marathon runner, the circularity of the system with repair becomes more apparent over the long run.
Precisely. It underscores the dynamic nature of circularity. It's not a static property. It's something that evolves over time, and the equations allow us to capture that evolution.
So how do the equations account for this circularity memory and the time it takes for that material to become unsustainable?
So what they do is they compare the circularity of the linear system and the repair system at 2 different points in time.
Okay.
The first point is when the material in the linear system reaches the landfill, right?
Okay.
The second point is much later when the material in the repair system finally reaches the landfill.
And at that later time point, the repair system has a significantly better circularity score. It's been in use for a much longer time, right?
Precisely.
Uh-huh.
Yeah. It highlights the dynamic nature of circularity.
It's really amazing how these mathematical models can capture these really nuanced aspects of circularity
Yeah.
and give us a framework for comparing different approaches.
It really highlights the power of a systems thinking approach when tackling this challenge of designing a more sustainable future. By considering the entire system and its dynamics, we can make more informed decisions.
So we've explored strategies focused on reducing material demand and introducing repair cycles. Are there other circular economy strategies that the paper explores or even mentions as, areas for future research?
Yeah, the paper briefly touches upon some other strategies and areas for future research.
Right.
One key aspect is incorporating energy efficiency into the models.
That makes sense.
Yeah.
Because even if the system is really great at, reusing materials, it might still consume a lot of energy in the process.
Exactly. We need to consider both material flows and energy flows
Right.
to get a holistic picture of the system's sustainability.
Right.
The paper also mentions the importance of considering time constraints.
Oh, yeah.
Because some processes in a circular system might take much longer than others, and those differences can impact the overall circularity.
Right. Like the time it takes to biodegrade a material or the time it takes to repair a product can significantly affect the system's dynamics.
Exactly. And of course, we need a more nuanced understanding of different materials.
Yeah.
Some materials are easier to recycle or reuse than others.
Right.
And those differences need to be reflected in the models.
This all makes me wonder about the practical applications of this research. Like, how can these models actually be used to design real-world circular systems?
That's a great question, and one that we'll definitely dive into in the next part of our deep dive.
Welcome back to the final part of our deep dive. So we've really gone deep into the math behind circular economy design. We've analyzed different strategies. We've even talked about the whole idea of circularity memory.
Yeah.
Now I'm really curious to talk about the practical side of things. Like, how can all of these models and these insights actually be applied in the real world?
That's the million-dollar question, right?
Right,
Like, it's
right.
all well and good to have these elegant mathematical models.
Right.
but they only really have value if we can actually use them to guide real-world decisions.
So how do we bridge that gap between theory and practice? How can businesses, policymakers, or even just individuals use these insights to actually design those more circular systems?
Well, let's start with businesses.
Okay.
Imagine a company that wants to make its operations more circular.
Yeah.
These models can provide them with like a framework for assessing different strategies, like reducing material use, incorporating renewable materials, implementing repair programs.
So it's like having a tool to compare those different approaches.
Exactly.
And see which ones would have the biggest impact on their circularity score.
Yeah, they can simulate different scenarios, analyze trade-offs, and make more data-driven decisions about which strategies to prioritize.
So it's not just about intuition or good intentions.
Right.
It's about having a quantifiable way to actually measure progress.
Precisely.
To make those informed choices.
Exactly. And it's not just about individual companies,
Right.
These models can be scaled up to analyze entire supply chains or even like industrial ecosystems.
Wow. So you could use these models to identify bottlenecks or optimize material flows between different companies and ultimately create a more circular economy at a much larger scale.
Exactly. And this is where policymakers come in. They can use these insights to create incentives, regulations, or infrastructure that supports circularity.
I can see how these models could even be used to evaluate the effectiveness of different policies, like, extended producer responsibility programs or taxes on virgin materials.
Absolutely. It allows for evidence-based policymaking, helping governments create the conditions that foster a more circular economy.
It sounds like we're talking about a paradigm shift in how we design and manage our economy.
It's
about moving away from that linear thinking and embracing something much more cyclical and interconnected.
Precisely. And it's not just about those large-scale systems either. These principles can also be applied even at the individual level.
That's interesting. How can individuals actually contribute to a more circular economy? Because it just seems like such a huge issue.
Yeah, it's all about awareness, and conscious consumption. By understanding the principles of circularity, individuals can make more informed choices about the products they buy, how they use them, how they dispose of them.
So things like choosing products with recycled content, repairing things instead of throwing them away, composting food waste, those all contribute to a more circular economy at the individual level.
Right. It's about shifting our mindset from a linear take, make, dispose mentality to a more circular reduce, reuse, recycle approach.
I don't know about you, but this whole conversation has been really eye-opening for me. It's made me realize that creating a circular economy isn't just some idealistic vision of the future.
Right.
It's actually a tangible goal that we can work towards using these data models and, smart design.
And it's not just about environmental sustainability either.
Right.
Circularity can bring economic benefits too. Like reducing our reliance on scarce resources, creating new jobs, fostering innovation.
It sounds like a win-win for the planet and the economy. What are your final thoughts for our listeners as they kind of continue on their own exploration of circularity?
So I would encourage everyone to think about the systems that they're a part of, whether it's their workplace, their community, their own household, and ask themselves, how can I apply these principles of circularity to these systems? What changes can I make, big or small, to promote a more sustainable and circular way of living?
That's a great challenge to leave our listeners with.
Yeah.
And it reminds us that creating a circular economy is a collective effort.
It
requires everyone, businesses, policymakers, and individuals to really get involved.
Absolutely.
Well, thank you so much for joining me on this deep dive.
Yeah, this was fun.
I really learned a lot, and I have a feeling we'll be revisiting these concepts again and again as the circular economy keeps evolving.
I think so, too.
Welcome back, everyone. Today we're doing a deep dive into something, something pretty fascinating, really. We're looking at the connection between circular economies and physics.
Yeah. It's not something you see every day, is it?
Definitely not. But a research paper by Zocco and Malvezzi, it's called Circular Economy Design Through System Dynamics Modeling.
Yeah.
They make a really strong argument for why these two things go together.
They really do. It's all about using math to understand and optimize how materials move and how we can keep them in use for as long as possible.
Exactly. And our listeners are all math whizzes, so I think they're going to love this.
Absolutely. They'll be right at home with the equations and models.
So where do we even begin with this paper?
Well, they start with this concept of a thermodynamical material network.
A TMN, for sure. Yeah.
Exactly. It's basically a way to map out the journey of materials from the moment they're extracted to their eventual end of life.
So kind of like a network of different stages.
Yeah, think of it like a flow chart. You've got your mines, your factories, your recycling plants, even landfills, unfortunately.
And within this network, materials are constantly moving and transforming.
Precisely. Being transported, processed, used, and, well, sometimes lost.
And it's those losses that they're really focused on, right? Those unsustainable flows.
Right. That's where their definition of unsustainable mass flow comes in.
It is.
Basically, any material that comes from non-renewable resources or ends up as waste.
So the stuff we're trying to minimize in a circular economy.
Exactly. And to measure how well we're doing, they introduced this idea of circularity, denoted by lambda, or
So lambda is like a score for how circular a system is.
you could say that. It's the negative sum of unsustainable mass and flow. So the higher the lambda, the better.
Makes sense. So designing a circular economy becomes an exercise in maximizing lambda.
Precisely. It's like a big optimization problem.
Yeah.
We need to find the best way to configure that TMN to minimize those unsustainable losses and get that lambda as high as possible.
And this is where the physics connection comes in. I have to admit, I'm still a little fuzzy on that part.
It's pretty mind-blowing, actually. They show that Lagrange's equation of motion, a fundamental principle in mechanics, can actually be derived from the first law of thermodynamics.
Wait, so we can analyze the movement of materials using the same laws that govern, say, planets orbiting the sun?
Exactly. It's a powerful connection that opens up a whole new way of looking at circular systems.
I can't wait to see how they apply this. Do they give any specific examples?
They do. They use 3 examples to illustrate how we can calculate and optimize circularity in different scenarios.
Perfect. Examples always help me wrap my head around these things. Let's hear them.
Okay, so the first one is what they call the linear case. This is like the traditional model where materials are extracted, used once, and then discarded. No attempt at closing the loop.
So pretty much the opposite of a circular economy.
Yeah, very linear, very unsustainable, and their calculations show that too.
What's the lambda for that?
For this linear case, it's a who represents the mass of the material.
So a negative value. Not surprising, I guess, given how unsustainable it is.
Right, and it sets a baseline for comparison with the other examples.
Okay, I'm ready for example number 2. What's next?
The next one looks at the impact of reducing material use, which is obviously a key principle of the circular economy.
Makes sense. So how do they model that?
They actually present 2 variations within this reducing example.
Okay, let's hear them.
So in the first variation, imagine a company that decides to incorporate 50% renewable materials into its products.
So like using bioplastics instead of traditional plastics.
Exactly.
That's definitely a step in the right direction. Does it improve their circularity score?
It does. In this scenario, they get a circularity of 1 is yielding 1.5 meters.
Still negative, but better than the linear case.
Right. It shows that even a partial shift toward renewables makes a difference.
That's encouraging. What's the second variation?
In the second variation, they focus on simply using less material overall.
So becoming more efficient with their resource use, regardless of the source.
Precisely. And in this case, they calculate the circularity to be 2 equal mesh of 1.6 meters.
Oh, interesting. So a slightly higher lambda than the first variation?
Yep, it seems that using less material overall, even if it's not all renewable, can have a bigger impact.
That makes you think, doesn't it? Okay, so we've seen the linear case and 2 ways to reduce material use. What's the final example?
The third one is where things get really interesting. This one focuses on robotic repair and the possibility of product reuse.
Ah, so closing the loop a bit more. This sounds promising. What's the lambda for this one?
Well, this is where it gets a bit tricky. Initially, when they plug in the numbers, they get lub equals 2 meters.
Wait, what? The same as the linear case. But we're repairing and reusing. Shouldn't that be much better?
It should, and it is, but there's a crucial factor they introduce here. Time.
Time. I'm intrigued.
The paper introduces the concept of circularity memory.
Okay, now you've really got my attention. What is circularity memory?
The basic idea is that we need to consider the entire lifespan of a product, not just its final destination.
So even though the material might eventually end up in a landfill, the path it took to get there matters.
Exactly. And that's where this idea of time comes in. They introduce a time horizon denoted by the Greek letter phi, or into their calculations.
So instead of just looking at whether a product is recycled or landfilled, we're looking at how long it stays in use before reaching that point.
Precisely. And when they do that, the results are pretty amazing.
How so?
Let's say we set that time horizon to the point where the material would have entered the landfill in the linear case.
Okay, I'm following.
The circularity for the linear case at that point remains mega just 2 meter, of course.
Right, because it goes straight to the landfill.
But for the repair case, it jumps to NEM.
Wow. So even though the material ultimately reaches the same endpoint, that repair and reuse stage makes a huge difference in terms of its circularity over time.
Exactly. It highlights the importance of keeping materials in circulation for as long as possible, even if they don't stay in use forever.
This is fascinating stuff. I'm really starting to see how these seemingly simple concepts like circularity have so much depth to them.
And we've only just scratched the surface. The real magic happens when they start using these mathematical models to actually design and optimize circular systems.
I can't wait to delve into that.
So are you ready to roll up our sleeves and get into the nitty-gritty of their mathematical modeling approach?
Absolutely. Let's see how they crunch the numbers to calculate those lambda values.
They start by diving deep into the linear case, that traditional take, make, dispose model.
Right, the baseline for comparison.
They actually use a geometric digraph to visually represent the system.
I noticed that, with all the compartments as nodes and those arrows showing the material flow.
Exactly. It's like mapping the journey of the material step by step.
And they even specified the geometry of each path, like the length and any slopes involved.
That's right, they really get into the details. So let's look at the actual mathematical representation of the system.
Okay, I'm ready for some equations.
All right, they define this linear system, NLL, as a set of compartments. It's a list that includes C11.1, C22.2, C33.3, C44.4, C51.2 series, C62.3, and C73.4.
Each of those represents a different stage in the material's journey, right?
Exactly. So C11.1 would be the non-renewable source, like a mine.
And then C44 would be the landfill at the very end.
You got it. And those in between represent the processing, manufacturing, use, and transport stages.
It's fascinating to see how they break down this seemingly simple process into such precise steps.
It allows them to analyze the dynamics of the material flow much more rigorously.
So how do they actually calculate the circularity for this linear case?
Well, they start by looking at the movement of a cube of material with mass.
Okay, so we're zooming in on a specific unit of material as it travels through the system.
Precisely. And to analyze its motion, they apply Lagrange's equation of motion.
Ah, that connection between mechanics and thermodynamics that we talked about earlier.
Exactly. It's a powerful tool that lets us treat material flow like a physical system.
So how does that equation actually play out in this case?
For the first compartment, C11.1, where the material leaves the source, they introduce a whole bunch of variables.
Right.
Things like Ft for the force of the truck transporting the material, F for friction and resistance along the path, MT for the mass of the truck itself, and MC5 for the total mass of the truck compartment.
Wow, they're really factoring in all the real-world details.
It makes the model much more accurate and insightful.
So what do they do with all these variables?
Well, they use them to define the kinetic and potential energies of the system, denoted by T and V, respectively.
Okay, I remember those from physics class. Kinetic energy is the energy of motion, and potential energy is stored energy due to position.
You got it. So T is calculated as 12 milli-C5 for CL5, where C represents the position of the material along the path and T is its velocity.
So they're using calculus to describe the material's movement over time. Precisely. And V is defined as MC5GVZT, which simplifies to MC5GST for the same range of thin. Hang on, there's some trigonometry in there. Okay. That means they're accounting for the angle of the path, right? Be sharp. They're factoring in any slopes or inclines along the way. It makes the model even more realistic. So we've got our kinetic and potential energies defined. What's next?
They then plug those into Lagrange's equation and take into account the non-conservative forces represented by STO, which is equal to the force of the truck, Ft, minus the friction and resistance, F.
Okay, so they're incorporating all the forces that are acting on the material as it moves.
Exactly. And all of that results in this second-order differential equation, MC5 sin plus FT for 35F, where sin represents the acceleration of the material.
Wow, that's a mouthful. But it basically describes how the material is moving along that path, right?
Precisely. And they go even further. They analyze this motion with respect to a reference frame, introducing equations for the second x, y, and z components of the material's movement.
So they're not just looking at the movement along the path, but also how the material's position is changing in three-dimensional space.
Exactly. It's a comprehensive analysis of the material's journey.
And they repeat this process for each compartment, right?
That's right. For every stage in the system, they meticulously define the variables, the forces, the energies, and derive equations that describe the material's motion.
It's impressive how they create this incredibly detailed mathematical model of the entire system.
It's a testament to the power of math to represent these complex, real-world processes.
So once they have this model, how do they actually calculate the circularity?
Well, remember that lambda formula we talked about earlier?
The one that defines circularity is the negative sum of unsustainable mass and flow.
That's the one. So they can now plug in the values for those unsustainable components, which they've derived from their detailed analysis of each compartment.
And that gives them a concrete number for lambda, representing the overall circularity of the system.
Precisely. And this is where it gets really powerful, because now they can start tweaking the model.
Tweaking it how?
Well, they can change the proportion of renewable materials used, or introduce a repair stage, or adjust any of the other variables that affect material flow.
And then see how those changes impact the final lambda value.
Exactly. It's like running simulations to see which design choices lead to a more circular outcome.
That's incredible. It takes all the guesswork out of designing for circularity.
Precisely. This mathematical approach gives us a concrete way to measure and optimize our progress toward a more sustainable future.
This has been an amazing deep dive into the math behind circularity. I'm really starting to grasp the power of this approach.
I'm glad to hear it. Now, are you ready to see how they apply this to those reducing scenarios? That's where things get even more interesting.
Absolutely. Yeah. Let's see how those efforts to reduce material use play out mathematically. Okay, so let's get into those reducing scenarios. I'm really curious to see how they model those efforts to reduce material use.
Right, so they start by revisiting this idea of unsustainable mass, denoted as MOOB. Remember, that's the part that really drags down the circularity score.
Right, because it represents the material that's either extracted from non-renewable sources or ends up as waste.
Exactly. So in that first variation, where they incorporate 50% renewable materials, their equation for unsustainable mass becomes mu B equals M2 plus M.
Let me see if I'm following this. Only half of the mass is considered unsustainable because it comes from renewable sources.
Right.
But the whole product still ends up in landfill. So that second M represents the unsustainable disposal.
You nailed it. And when they plug that into the circularity formula, they get Lu1 equals 1.5 Miller.
Still negative, but definitely an improvement over the linear case.
Right. It shows that even a partial shift towards renewables can make a difference.
That's good to know. What about the second variation, where they just use less material overall?
So let's say they manage to reduce material use by 20%. The equation for unsustainable mass then becomes semi 0.8 meter plus 0.8 meter plus 0.8 meter equals 1.6 meter.
So both the extraction and the disposal are reduced proportionally.
Exactly. And that leads to a circularity of R2 equals M minus 1.6 meter.
Interesting. It's actually a slightly higher lambda than the first variation, even though it doesn't involve renewables.
It highlights that reducing material use in any way we can is a powerful lever for improving circularity.
Absolutely. It's all about minimizing our impact at every stage of the product life cycle. Okay, now I'm ready to dive back into that third example, the one with the robotic repair and circularity memory.
The one where time really comes into play. Remember, they start with this modified system NP, which includes that repair stage. But at first glance, the circularity help still comes out to mixed 2 meter, the same as the linear case.
All right. It was a bit of a head scratcher until they introduced that idea of circularity memory and the time horizon.
Exactly. So they bring in these new terms, LOL and LOP, to represent circularity with memory for the linear and repair cases, respectively.
With that subscript, reminding us that we're evaluating circularity within a specific time frame.
Precisely. And if we set that time horizon to the point where the material would have entered the landfill in the linear case, we see a clearer difference. Low MOMA 70 meter for the linear case as expected.
Right, because it goes straight to the landfill.
But for the repair case, it's low MOMA the 70 L in the lowest MOMA.
Wow, a significant improvement. Even though the material eventually ends up in the same place, that repair stage makes a huge difference within that time frame.
Exactly. And they actually quantify this difference with a term called RE, which represents the time extension achieved through those repair and reuse stages.
So that time extension is really the key to boosting circularity.
Mhm.
It's about delaying the need for new materials and keeping those existing materials in play for as long as possible.
Couldn't have said it better myself. This paper really showcases the power of thinking about circularity in a more dynamic way, considering not just the end-of-life fate of materials, but also the entire journey they take.
Absolutely. It's a fascinating and insightful approach.
And the beauty of it is that it gives us a really tangible way to measure and optimize our progress towards a circular economy. We're not just relying on intuition anymore. We have these powerful mathematical models to guide us.
It's been an incredibly enlightening deep dive. I'm walking away with a whole new appreciation for the power of mathematics to help us design a more sustainable future.
I'm so glad to hear that. And I hope our listeners are feeling inspired to explore these ideas further. There's so much more to discover in this exciting field.
Thanks for joining us on this deep dive into the world of circular economies and physics. Until next time, keep those circular thoughts spinning.